Alright, this video is going to be on how to find the limits for piecewise functions and absolute value functions. And we have looked at these a little bit graphically, but we haven't looked at how to do it algebraically, and so that's what this video is going to focus on, is how to do that algebraically. So first, I want you to recall that a limit exists. A limit exists when the limit as x approaches a from the left side of a function is equal to the limit as x approaches a from the right side of a function. So that is the formal notation way of saying that the left and the right hand limits agree with each other. So when we look at these functions, this is going to be something that's going to be our trick to being able to do these functions by hand if we don't have a graph of the function to reference. So first, we'll go ahead and start with the piecewise portion of the notes. And our first example is going to be using the piecewise function. F of x is 8 minus 2x if the x value is less than 4. And it's going to be the square root of x minus 4 if the x value is greater than 4. All right, so the first limit we're going to find in relation to this piecewise function is we're going to find the limit as x approaches 0 of the function. And just like we did before, anytime we are solving a limit algebraically, we always want to see if this number is in the domain of that function. And in this case, it is. 0 is a number that shows up within these x values. So since 0 shows up, I have to figure out which piece I'm going to use to plug it into. And 0 is defined for the first equation. 0 is less than 4. It's defined there. So that's where I'm going to use it. I'm going to say the limit as x approaches 0 of the first piece of the function, because that's where I can plug it in, should be 8 minus 2 times 0 would be 8 minus 0. So the answer is 8. All right, for another example, let's say we wanted to find the limit as x approaches 8 of the piecewise function. Again, when I look, I can see that 8 is in the domain of that piecewise function, and so I just have to consider which piece I should plug it into. And this time, it's the second piece. So the limit as x approaches 8 of the second piece of the piecewise function, you have the square root of 8 minus 4, which is just the square root of 4, and so that's 2. So anytime the number you're finding the limit of is within the domain, you can just use direct substitution, and it's pretty easy. Next, we'll look at one that's a little bit more exciting. So we're going to say we want to find the limit as x approaches 4 of the function. Now, this is the only x value that we had that was not defined in the domain. We have if x is less than 4 and if x is greater than 4, but we don't have anything for x is 4 exactly. And that means there's no clear place for us to plug 4 in to get just a single answer by itself. So in this situation, we're going to go ahead and find the left-hand limit of 4 and the right-hand limit of 4 and see if those two numbers agree with each other. So first, I'm going to find the limit as x approaches 4 from the left side. And if I'm approaching 4 from the left side, that means I'm going to look at the piece of the function that has x being less than 4, because that would be the left side. And then to do the right-hand limit, I'm going to say the limit as x approaches 4 from the right side, which would be the other piece. And now I'm going to go ahead and evaluate each of those and see if those two numbers agree or not. So 8 minus 2 times 4 is also 8. So 8 minus 8 is 0. The square root of 4 take away 4 is the square root of 0, which is also 0. And because those two limits are exactly the same, we are saying that they agree. And that means that the limit as x approaches 4 overall of this function is 0. So the limit here does exist. All right, next we're going to look at the absolute value portion of the notes. And here we want to recall that if we have the absolute value function f of x equals the absolute value of x, I can actually rewrite that as a piecewise function. So I'm going to go ahead and draw a little sketch so we can reference that. If you guys remember absolute value functions, they typically start at the point 0, 0, and they go to up 1 to the right 1, up 1 to the right 1, up 1 to the right 1, and up 1, left 1, up 1, left 1, up 1, left 1. So if I want to not call this an absolute value function, if I want to rewrite this as a piecewise function, I can do so. I just have to look at it as the left side of the function, which would be negative x, and the right side of the function, which is positive x. So I've written both of those with a slope of 1 and a y-intercept of 0, and I'm just showing that one of them has a negative slope and one of them has a positive slope. And I'm going to go ahead and say that this one is if x is less than 0, and this one is if x is greater than or equal to 0. It doesn't matter where your equal to part goes, it just needs to go with one of them because this point is included. All right, so when we look at absolute value functions, we're actually going to think of them as piecewise functions instead. So, for example, let's say we want to find the limit as x approaches negative 2 of the absolute value of x plus 2 divided by x plus 2. And if you look here, negative 2 for an x value is not within the domain of the function. It would make the denominator equal 0, and we can't have that. And so that tells us we need to do some more work. So what I'm going to go ahead and do is I'm going to write this as a piecewise function. So I'm going to say f of x is negative of x plus 2 divided by x plus 2 if the x value is less than negative 2. And the reason I know that this is the x value I'm talking about is because that is where the vertex of that absolute value would have been. That's where it's going to switch directions. And then I'm going to say that it would be positive x plus 2 over x plus 2 if x was greater than negative 2. So that's my piecewise function right there. Now at this point, I can look at this piecewise function from the left and from the right side. So the limit as x approaches negative 2 from the left side would be using this first function right here. And then I'm going to look at the same thing as x approaches negative 2 from the right side, and this time I would be using the second part. And if I look here, now I can see that these two factors would actually cancel out. So I can say it doesn't matter what I plug in for x, no matter what I plug in, this is going to end up equaling negative 1. Because those two factors cancel out. Over here, these two factors also cancel out, so no matter what I plug in, this is going to equal 1. And it was necessary for us to do that step of canceling the factors because negative 2 is still not in the domain even though I've simplified this. Even though I took the absolute value away, I still had something that was not within the domain. So I had to think of canceling those out. So when I look at this, the limit from the left side is negative 1, the limit from the right side is positive 1. They do not agree. So that means that our overall conclusion is that the limit as x approaches negative 2 of the function does not exist, and our reasoning for that is two different values. All right, we're going to go ahead and do one more example for absolute value. We're going to take the limit, we're going to find the limit as x approaches -4 from the left side